Hi, today we'll be looking at how Mars, with its bolt static analysis module, can help you design bolted joints for complex mechanical systems. Complex mechanical systems contain many bolted joints, and for the purpose of correctly designing them, people usually analyze them in groups based on common characteristics such as bolt orientation, classification, size and material, mechanical loads, torque installation settings, clamping configurations, and clamping materials and sizes. To demonstrate how Mars comes into play, we will be using an optical payload with several bolt groups as an example. During a design phase called qualification campaign, such a payload would be subjected to a physical test consisting of random vibrations induced with the help of a shaker table. The vibrations generated by the shaker table induce forces or loads into the bolts that keep the optical payload together. Therefore, the bolted joints of such a mechanical system must be sized correctly and verified in advance in accordance with industry standards such as ECSS and VDI to ensure the system will survive such a physical test. So why is it that CAE software cannot do this verification? Well, in the normal process of designing a mechanical system, you would first build a CAD model containing all the details of all the components. Then you would build the FEA model based on that CAD model, and then you would perform simulations on that FEA model under different scenarios. But it's not feasible to build the FEA mesh to cover the entire system and to be fine enough to capture the small details such as the thread of a bolt. So you get around this problem by building a coarser FEA model which accounts for a bolt only as a 1D spring element. This way you obtain the forces which the bolt is subjected to and use them into a separate software which accounts for all detailed characteristics of the bolt. To demonstrate how Mars would be used to verify bolted joints, we'll use the model of an optical payload, which is part of a satellite. The model appears quite simple because some of its details were removed due to confidentiality reasons. This optical payload is tested by mounting it onto a shaker table, which induces vibrations of various frequencies and magnitudes, simulating the vibrations which would be experienced by the system when it's launched into orbit. We are going to focus on the bolts used to mount the optical payload to the shaker table. These bolts must be verified to ensure that they will not fail during the test, thus causing damage to the component being tested. The verification consists of determining the margins of safety, which depend on the bolt size and material, the number of bolts included in the mechanical system, and the load experienced by each bolt. And the breakdown of the model is as follows. We have the optical payload itself, highlighted now in yellow. This is bolted down to an interface plate using a clamping band and two clamping rings, 1 and 2. And the interface plate is in turn bolted down to the shaker table, which is not present in the model. Between the two clamping rings and the clamping band, we have 8 bolts with hexagon head. These ones here. Then 12 bolts between the clamping band and the interface plate. These ones. And 16 more bolts between the interface plate and the shaker table, which go on the bottom into these threaded holes. In the finite element model, the bolts are modeled with the most common element type, which is a 1D spring element with 6 degrees of freedom. In the finite element model, the bolts are commonly split and subsequently analyzed in groups. For example, all identical bolts which clamp a certain component will go into the same group. The information about these groups can be exported from NXIM Center into a text file, which Mars can then import to help speed up the data input. Even after remeshing the model, Mars recognizes the bolts in each group based on the group name, assuming the name remains the same. Once the text file is imported, Mars updates the bolt element IDs in the analysis to match the load input data. I will now generate a text file containing the exported information and then explain its contents. So we first hide everything and only show the meshings of the spring elements. We select all of the spring elements, click here on node element, and then click OK. So we have the bolt group name, also called mesh collector. This is specified by the user when building the finite element model. An XSIM center allows this information to be specified, and it's usually a good practice to do so, to make it easier to identify the different connections available in the mechanical system. Element ID or label, which is a unique identification number for each element used to represent a bolt. The element type used to represent a bolt. The most used type is C-bush, which is the 1D spring element with 6 degrees of freedom. Other types include 1D bar or beam elements. These differ in the way they are formulated and in which their response result is reported. And finally, connected nodes, which contains the IDs of the connected nodes of each element. The user should pay attention to the axis of the coordinate system along which a bolt is positioned, x, y, or z. This influences the axes along which the axial and shear forces of the bolt are reported. Mars is designed to be extended to allow importing information produced by any finite element analysis software, and we can address this according to the user's needs. The bolt static analysis module of Mars is structured as follows. We have analysis settings, which is the main view where the user can define most of the calculation parameters. The bolt groups from the model are defined in this list. And for each group, we have the bolt counterpart and washer properties, properties of clamped flanges, bolt axis and temperature variations, IDs of bolts included in the group, and bolt coefficient of utility and friction coefficients. Load data is the view where the user can import bolt forces produced by a finite element simulation. Currently, importing is possible from punch, F06 and CSV files. If needed, support for any other file type can be added upon request. And safety factors, which is the view where the user can define the factors of safety that need to be taken into account when performing the margin of safety verification. The bolt static analysis module has two modes for margin of safety verification. A comprehensive mode, which is this one, and a simplified mode. You can switch between these two by going to the Options menu. The comprehensive mode performs all necessary calculations starting from the mechanical characteristics of the bolted joint components according to the applicable ECSS and VDI standard. While the simplified mode is used for verifying margins of safety when the compliance value of bolted joints and optionally the bolt preload and tensile strength are already known, for example from a physical test or a simulation. In order to perform a verification, we have to start by defining the bolt groups, and we can do that in two ways. The first way, we can right-click on this list and select Add New Group. Then we double-click the group name and rename it to something like Bolt Group 1. And we can carry on like this, creating all the necessary groups here. Then for each group, we move on the right side and input all the necessary settings. Now, in case we already have all of this information available in a text file because we were able to export it from our finite element analysis software like Siemens NX. And in this case, we have the bolt group name under this column, mesh collector, and the assigned element IDs under the column label. We can import the information directly by right-clicking here and selecting Import Bolt Groups from File. And you can see it's imported all of the groups. And for each group in this list here on the right, we have the assigned element IDs. One notable option is update element IDs from file. Now, if you have to change something in your mechanical design, and due to this, you end up reassigning element IDs to different groups, or adding or deleting elements from groups, you can re-export the information into the text file, and then select this option, select the text file again, and all of your element IDs will be updated for all of the groups. Now let's make the settings for one of the bolt groups. And we're going to start with the bolt properties. Now for the purpose of this demonstration, I will just make some random settings, and then at the end I will load the real settings from a file that I have saved. For the bolt, we have to define the geometry here on the left and the material here on the right. And Mars comes with a database of predefined components and materials for these components. The predefined components are bolts, nuts, helicoils, and washers. So from this list of predefined bolts, I'll just select one, let's say this one, and from the materials list, I will select this one. Now, if you find that the component or the material that you need is not already defined, you can easily define your own. For instance, you can start from one of the predefined ones. And as an example, I will change the threaded length here to, let's say, 50. And now you will notice that here it says custom. This is because this bolt in this configuration does not exist in the database. And you can easily add this to the database for later reuse by clicking this button. And you have to input the name for the bolt, for the new bolt. And I'll call it custom bolt. And the standard. And I'll just input 1 here. So you can see that now we have it here. And it's added to the end of the list here. So we can select it in the future. I'll just make the initial selection here and click OK. Here you will notice that there is a summary of our bolt properties. And in the first row we have the geometry, and in the second row we have the material. In the first row we have the bolt specification here, so this is the name of the bolt, the length of the bolt, and the pitch of the thread, and then the standard. And for the material, we have the name of the material and the standard here. Now let's define the counterpart properties. For the counterpart, we have 3 options to choose from. We can either specify it as a nut, or we can specify it as a threaded insert. And this is the case if the bolt is threaded into the last plate that it's clamping from the stack, or threaded insert with helicoil if we have a helicoil in the thread. If we select the nut option, then we can come here and select the predefined nut and a predefined material for the nut. If we want to select the threaded insert option, you will notice that these controls are disabled. And this is because for this option, the material will be that of the last plate that the bolt is clamping. So essentially the plate it is threaded into. And the same for threaded insert with helicoil. But in this case, we get some extra options to specify the helicoil. So I'll just select one from here. and one option for the helicoil material. For the washer, we have to first specify the washer setup. So we can either not have any washers, or just have a washer under the bolt head, or a washer only under the nut, or both under bolt head and under nut. In this case, I'll specify under bolt head, and you will notice that now this button becomes available. Go into this window, and again, we can select from a predefined list of washers and from a predefined list of materials. The last piece of the setup is the plate stack, and we can define them by right-clicking on the list and selecting Add New Plate. Here we have to select the material of the plate or define our own, and we have to specify the thickness of the plate. And in this case, I will define 2 plates as an example. And you can define in this list as many plates as you have in your setup. In case you don't have the bolt groups information in a text file to be imported and you need to define the element IDs for the group manually, you can do that by right-clicking on this list, and here you have 2 options. One is add IDs from data, and this list will be populated from any IDs which are defined in the data that you have loaded. Now, in my case, I don't have any IDs because I haven't loaded data yet, but you would be able to select the IDs from here, or alternatively, you can add the IDs manually, and you can specify them, for example, as an enumeration or as a range. So I can say, for instance, 17, 18, and then 20 to 25. And you will notice they've been added here to the list. Lastly, we have a host of other input parameters to set. Include moments specifies whether or not the moments in the data that you will be importing should be included in the calculation or not. Then we have the bolt axis, and whatever axis you choose here for the bolt, the software will consider the forces in that axis as being axial force, the axial force, and the forces in the other 2 axes as being the radial forces. Then we have some parameters for negative and positive temperature variations that should be taken into account. We have some parameters here for how close the bolt is to the edge of the plates. And this is important because if it's too close to the edge, it can rip through the plate more easily. We have the bolt coefficient of utility, and then some friction parameters here between the bolt head and the first plate that it's clamping, between the plates themselves, and between the bolt thread and the counterpart. Let's now have a look at the load data view. So here we can import data from 3 file types currently, which is punch file and F06. These 2 file types are generated by the Nestron solver, and then we have CSV as well. We can obviously add functionality to be able to import data from any file type here upon request. I'd like to show you an example of importing data from a CSV file. So we have this file here where we have the first column being the element ID. The second column is the subcase, the analysis subcase. And then we have 3 columns for the forces in 3 directions and 3 columns for the moments around these forces, these directions. And if I select the file from here, we get a pop-up where we have to specify the order of the columns in the file in case they are in a different order. And in this particular case, they are, because the element ID is the first column. And we have to specify the first row of the data. In this case, it's 2, so we're okay, and we can import the data. Now we have some options. If we right-click on this list, we can choose to scale all of the data by a certain scale factor. And in this case, I'll choose 1000. And you can see that all of the values have been multiplied by 1000. I'll just scale it back. And we can also delete individual rows if we don't want them, or we can export data back to CSV file. And this might be useful in case you've imported data from one of the other file types. And I'd like to show one more example of importing data from a punch file, which I have here, which is just over 800 megabytes. So the software parses the file and then it gives us a choice with a list of all of the data sets which are available in this file. And we can either choose some of them as we wish, or we can choose all of them. One other feature that we have here is the ability to edit individual values in the data. So for instance, I can double click on this and I can change it to whatever I want in case you want to edit this data. One more thing to note here is that the software assumes all of the forces to be in newtons and all of the moments to be in Newton meters. And the third view that we have available is that of the safety factors. And this is pretty straightforward, just some values for a host of safety factors that can be taken into account when running the analysis. So once you've made all of your settings for all of the bolt groups, you can go to File and then click Save. And you can save all of the settings into one file. I'll just call it demo in this case. And here's the file. I have to mention that this file will also contain any data that you have loaded here. So you can easily share this file with colleagues that may need to look at what you've done, or maybe tweak the inputs a little bit and rerun the analysis. So now I will upload the correct settings, because as I said in the beginning, whatever I put in here was just random for the purpose of the demonstration. So we can either go to File Open, or we can simply drag and drop this file onto the bolt groups list. And now all of the groups have the correct settings made. So we are now ready to run the analysis. We click on Start Analysis and then Show Results. And the report is generated into an HTML file which opens in the browser. It starts with a verification compliance summary table that lists the margin of safety verifications performed according to the ECSS and VDI standards. This is followed by a top-level summary of the worst margin of safety values calculated for each bolt group. Clicking on the group name here takes you further down to the detailed verification report for that group. We have a list of the applied safety factors, friction input parameters defined for each bolt group, preload summary for each bolt group, slipping margin of safety based on the average shear and minimum clamping force for each bolt group, then a detailed verification report is included for each bolt group containing the margins of safety, torque installation settings, the input settings for the bolt, for the washer, for the counterpart if present, and for the plate. And lastly, we have a table of further parameters calculated by Mars for the bolt group. And then it continues with the next bolt group. Now this HTML file is actually a Microsoft Word friendly file. So you can also open it in Microsoft Word and it would look exactly the same. You would have access to the headings in the navigation pane and you would be able to edit or copy and paste information. And you would also be able to save this into a Word file, so essentially changing the format from HTML to Word. Let's also have a look at the report for the simplified case. So for the simplified case, we have two options here. For the first bolt group, we've specified manual bolt preload and tensile strength. So this means that we might have these values either from an experiment or from a simulation, and then whatever bolt properties were input here are ignored. And for the other bolt group, we have automatic calculation of bolt preload and tensile strength based on the bolt properties defined here. Now the report for the simplified case is a reduced version of the comprehensive report, and it includes a top-level summary containing the margin of safety for slipping, gapping, axial yield, and ultimate strength, the applied safety factors, which are fewer than in the comprehensive case, friction input parameters, preload summary with slightly less details, namely it's missing the last table, slipping margins of safety, and then details for each bolt group. So detailed margins of safety and bolt input settings, which for the first group were these parameters, the bolt preload and tensile strength. And for the second bolt group were the bolt properties. So this was our bolted joint analysis demo with Mars. Thank you for watching and please get in touch if you would like to receive a trial version of Mars.